Hello, fellow Karnaugh map enthusiasts. This is the fourth and tentatively final installment in the series of Karnaugh map videos. Last video, I showed you my recursive view on Karnaugh maps with the same kind of logic. And this video is going to take into account the first part of it. Um, Now, one thing, if you've stuck with me all the way through here, um, I think you might have fun. I'm going to become a little bit more informal. If you haven't, and you just stumbled upon this video, I suggest you watch the other ones first, because this requires at least a third video if you're comfortable and familiar with Karnaugh maps, okay? So, let's just get started. Oh, one thing though. The same disclaimer, maybe somebody else stumbled upon this, and if you did, just send a comment, type in a comment or anything, I'll give you the credit you rightfully deserve, and I'll be more than glad to look at your work if you have an abstract, or even better, if you could actually share the source, that would be awesome. So, let's just go on. Okay, so we're going to tackle 7 literals, but from a different angle, okay? So back to the old 6 literal map. I really like this map because it's two-dimensional, nothing's repeated, and it's just eye candy to me. So what we're going to be doing is we're going to distort it in an entirely different manner. Now I'll be exploring 2 different approaches for the moment. First, we're going to place a little square inside, and the other way is we're going to use a trapezoid split, which is very nice because it's very easy to draw even if we had really ridiculously hideous lines. So let's try both of them. So in order to draw the square, we just draw the square and we have the problem that we actually need a good pulse. Now, drawing the trapezoid is an entirely different manner. We just take the same places where the lines intersect the edges and follow the lines. I like that because I have a very horrible handwriting, and having something that helps me make a readable output is quite a bit of a relief. Okay, so that's nice, but what does this stuff mean? Well, it means we're now in the 3-dimensional space. We now add an in and out dimension. So we have left, right, up, down, and in, out. So how does this actually work? Well, now we see the entire diagram with something. So, in and out are neighbors. And if it's in, then up and down are neighbors. If it's out, then outward, up and down are neighbors. It's the same thing. Okay? So let's see. This solution is pretty much understandable, huh? I hope this is self-explanatory. And yes, we have the 4 ones inside the in part. Well, we group those. And if the whole thing is filled with ones, well, we can group it. Okay? So, this is how the entire diagram looks like now. Nice, huh? And this is how the other diagram looks like. I find the inner square approach a little bit more pleasant to the eye, but unpleasant to my hand. But, later on I find the other one more helpful than what's to come, which is 8 literals. And now it's going to get particularly bizarre. So those of you who love, this is why I put this artwork, if you ever wondered. Well, I just got inspired by what's to come. So we first have to split them in 2. So how do we do that? Well, we can just type a big cross and that'll take care of it. But what have we done? Well, I like to think of this extra degree of freedom as a gyration. We can now rotate clockwise and counterclockwise. And if we look at it this way, well, we just have to position ourselves right in one of those corners and then just gyrate. It's kind of simple, right? So Here's a more down-to-earth example. We just pick one of these places. Let's just say we're going to pick that right up inner square. And we just have to make sure that the part that points towards the center is pointed down in our minds. And that's it. We just position ourselves on top of it and rotate either clockwise to the white area or counterclockwise to the blue area. How does this apply to the other one? Well, it's the same thing. And really, we just position ourselves in one of these places and then just in our minds make it, just put it on top of the table. Then we just rotate to one side or the other. Okay? I find this a lot more appealing since the patterns don't repeat themselves. But that's just me. Okay, so how does this actually work? Well, these are some of the valid relationships. As you can imagine, things that are clockwise and within the same part of the diagram get to be neighbors. Same logic that we always have been using. Okay? Which one to use? I'll leave that up to you. So let's look at it. Alliterals with the trapezoid split. I find this rather nice. Now, as you can see, I started using a little bit of dashed lines to do that because I found it a little bit intimidating with the same kind of lines. There were just too many lines. But when I did this, I found it very easy to put my mind into it and understand this four-dimensional diagram. So what about the inner square? Well, the inner square isn't that bad. One thing, though, as you can see, my drawing abilities have reached the point where they're not necessarily so great. It had to happen. I mean, these are not precise drawing tools. This is not a CAD program. So the idea is this, okay? So, more power. Well, yeah, but first, let's just think about this, okay? We can go further doing the same kind of thing, but it's not really practical. So why should we do it? Because it's kind of fun, because we want to see it. We want to make sure that it's possible. Well, that's why people actually must have climbed the Everest. I mean, it's cold, it lacks oxygen, and they still did it. And many of them died on the way and lost a lot of money. But they wanted to see if they could. So let's see if we can. So how do we add more? Well, here it is. Follow the arrows. And the other one, just draw these lines. Pretty simple, huh? So let's see what end result we have without those colors. Interesting, huh? We have two fractals. So let's look at number 10. The inner square is a lot more complicated right now. But I think we're both starting to see how this goes, right? So let's see. Beautiful, isn't it? Okay, 11 and last. Seems like the center becomes more and more complex while the edges slowly catch up. So we're kind of like having this really sophisticated center and this relatively slow edge. I kind of like to think about it as this very far away situation, but fractals are pretty much that, just something that is self-similar. And we have something that is becoming self-similar. So what about the other one? Well, actually, I just took 4 of them, put them together, and this works. Guess you already saw that, huh? But it was fun, isn't it? Yeah, maybe not. Oh well. Anyway, so we still have one more. I still have one more thing to tell you guys. One more attempt at insanity. And I'm going to call this the asterisk. Now, what happens if we just go ahead and press and draw a cross inside? Well, we just applied the gyration logic, clockwise and counterclockwise. We already explained a while ago. This is why I just wanted to cover this later on. So, how do we make this one evolve into a strange and unnecessarily complicated figure, well, we can just add lines, but that wouldn't be much fun. What we'll do is add these other lines. Rather than just split them into different sections, we're just going to split them horizontally and then vertically. And now we have a pattern forming again. An interesting pattern, I'd say. This isn't really a fractal because it isn't really self-similar, but it is a pattern nonetheless, and a very interesting one, I'd say. And as you can see at 11, it is very complicated, but it is not as complicated as the other ones. And at 9, it is simpler than the other ones. Let's just take a look at them at 9. Okay? So, what next? Well, that's pretty much it. But let's go back a little bit. We have 12 by embedding Karnaugh maps, plus 2 or 3 with the methods we just described, plus 2 folding. We've surpassed the 16-bit mark. A very good number for embedded systems design. And the important thing is 8-bit is actually very feasible. It's actually pleasant to look at. And 17 is a lot greater than the 4 that we're usually taught, right? So, what did we accomplish? Well, we had a review of Karnaugh maps, but if you went all the way over here, you're most likely didn't need it. Rather than that, an in-depth analysis of uncommon and potentially original, I'd hope. Multiple end-input Karnaugh maps, which were reviewed, and from these we have extended the conflict zone to 8-bit design, which is actually important. Plus, we saw some pretty pictures, right? Okay, so last off, I'd like to give you some references. There's this digital design book. This is the basis. There's discrete mathematical. That was the glue. The discrete mathematical structures. That was the glue that held everything together. You know, not that I was applying it, but I read it before and I went through it, covered the cover, and I liked it a lot. And it gives you a little bit more of a language and a little bit more of the custom of what represents a relationship. And there's the digital, these ones are in Spanish, digital image, digital, artificial vision books. These are important because the approach I used was basically the same as the classical mask approach or the classical artificial vision problem solving. Now, I'd like to also nod to Stephen Wolfram's book. I think it has a lot of interesting information in it, and thanks to I'm still reading it. I did the first few exercises, and that more or less gave me a different perspective that allowed me to actually have the creative engine that brought all of these things together and made this presentation possible. Now, I'd like to thank you a lot for your attention, and I'm really looking forward to the comments you guys have. I'm sure you have some very interesting insight. I hope you enjoyed this. I hope this somehow helps you or inspires you to do something completely radically different to the point where I can't even recognize any inspiration from my own work. And if so, I hope to have some kind of video response or just comment, hey, look, I got this really weird idea, and I'll be more than glad to actually look at it. Okay, so thank you very much again, and hope you had a great time, because I sure did. I'll see you around in a different subject, non-related video. Okay? Bye.